Okay, so this is our trickier problem. We've got to take a 10 kilogram wooden block, place it on a 45 degrees smooth slope, so no friction. We've got a light inextensible rope, so no stretching, no weight, passing over a smooth pulley, again no friction, and that's going to a 5 kilogram mass hanging vertically at the other end. And what we're going to have to do is we're going to have to draw two free body diagrams and then determine the acceleration of the system. So step one is going to have to be actually drawing the system diagram. And the system diagram looks a bit like this. And we have a 45-degree angle in here. And our red block is 10 kilograms, and our blue block is 5 kilograms. So let us first consider just the blue block, the 5 kilogram block. Now, obviously, the only forces acting on this must be, to start with, its weight, which is going to be 5g downwards, and there's going to be an upwards pull, let's call it T, from the rope. Now, we can assume that the whole thing is either going to be in equilibrium or not, and so let's just, for argument's sake, assume that this is going to move downwards. So let's say the whole system is moving downwards with acceleration a. So let us now consider our 10 kilogram block. Well, here's our 10 kilogram block without the slope, and obviously it's got its own weight coming down of 10g, and we know it's not falling into the side of the slope, so 90 degrees to the slope there must be this normal reaction force, let's call it R, and pulling it up the slope must be the rope. Now the rope is the same rope as before, so it still must have a tension T. We've called it T prime here because it's the same size, opposite direction, and we know that's true because the rope is not stretching. And if we said our blue box was going to go down, then our red box must go up with the same acceleration. Okay, so now it's time to do the math. So we're going to use Newton's first and second laws, which basically says that the sum of the forces is the mass times the acceleration. And first of all, we're going to consider the blue block, which confusingly here is in green text. And if we consider the vertical forces, then we can say that the upwards tension minus the downwards weight equals the mass times the acceleration. And if we arrange that so it says T equals, you get this expression here, 5g plus a. Now if we go on to the red block and consider just the forces going along the plane, so parallel to the plane, and do exactly the same thing, then when we do that, we get this beautiful equation here, which says that the tension in the rope minus the parallel component of the weight equals 10 times the acceleration, which again can be arranged so it says T prime equals 10 brackets a plus g sine 45. Now we could work out what g sine 45 is and leave it as a number, but it will be easier to work with algebraically here. So the next step is not particularly hard, and that is to say that T equals T prime. And we can say that because we know the string isn't stretching, and we know the string is light and doesn't have any weight. So if that's the case, then we can also say that this is true. 5g plus a equals 10a plus g sine 45, which isn't particularly nice, but obviously there's a common factor of 2 in there, of 5 in there, so we can take that away and replace it with this version. Now, if we bring all the g's and all the a's together, so the g's are on the left and the a's are on the right, we end up with this equation, which obviously on the right hand side can just be simplified to a. Well, at this point it's just numbers, so therefore our final acceleration is a equals minus 4.0634 meters per second square. Now notice the minus. This obviously means we got our original direction wrong, which means the 10 kilogram block slides down the hill rather than sliding up the hill.